Thank you.
Yes.
Thank you. Yes, so now we switch to more fundamental science after this very applied research. And I will talk about grain coarsening, which appears in metals at room temperature because of cyclic mechanical load. And this effect is a kind of controversial because on the one hand, there are really plenty of papers showing that that happens. That at room temperature in different materials and different loading condition, like indentation or beam bending or tensile loading, grain can grow at room temperature. On the other hand, there are many people, or probably each of us, has this strong, deep belief that grain growth, grain coarsening is a thermal activated effect. Because that is what we learn from all nice textbooks. So, and of course today I will show you that indeed it can happen at room temperature only due to mechanical strain. And I will show you two cases, both on polymer supported films, copper and gold. First, rather like a side effect, what I call here, and then I will go in more detail, showing detailed DBSD analysis, and I will present a model which tries to explain what we observe. So let's start with copper film. Before, I would like to make a remark. Although we are dealing with applied research about the fundamental mechanisms, there is a very strong application in the background, and this is flexible electronics, where you need to have metal films on polymer substrate, at least to conduct lines, to conduct current, or probably with other functionalities. So that's why we, during our mechanical test, we're not only looking at the surface and at the damage and cracks and extrusions and so on, but we also record electric resistance during the test. And the second reason is that this is a very, very powerful and very effective in situ technique. In my opinion, the most effective in situ technique, because all you need is just to introduce the grip, the contacts in the grips, and then you can do your test and you have electric resistance recorded simultaneously. We applied sine strain function between 0 and peak strain and record electric resistance during the test. And that's a typical outcome. So we have 500 nanometer copper film on polyamide. This is a polymer. And if you look at the resistance, this is a recorded resistance divided by initial value. You see a very typical and expected behavior. After some cycle number, the resistance starts to grow very steeply, and that is indication of the cracks. The good thing, again, about resistance is that if you do SEM, you might not see the cracks. In most cases, you will not clearly see the cracks because copper is ductile material. What you see are more or less extrusions from the top, and if you want to see crack, you should cut it with a fin. So you either have to cut all the extrusions, but from this curve we already know that the damage is induced in the form of cracks. Then if you make the test with 1% peak strain, for example, then again something expected. We have lower resistance increase, we have lower damage on the isolated extrusion and cracks, so everything is logical and even a bit trivial. What is, however, untrivial is what happens here in the beginning. You see that resistance decreases, actually. And I was fighting for several months against this what I thought artifact, experimental artifact, because it's very unlogical. Why should it decrease if you apply mechanical load? But it was always there, so we started to look more details at the microstructure. This is a typical bimodal grain size distribution microstructure of this copper film. We have large grains, and we have these almost nanocrystalline grains, around 100 nanometer, and larger grains about 1 micron. Then if you look at the same place after 10,000 cycles with 1% peak strain, by the way, the loading direction is always horizontal. You can see that the area of these nanocrystalline grains is greatly decreased and can be seen better in the grayscale image. It's the same. I just show here with black all the grains which are below 250, and the coverage decreases from 50% to 20% here. And those only small grains are responsible for increased resistance, increased scattering of electrons. That's why we believe that exactly this grain coarsening effect causes the resistance decrease. But then we proved it finally and totally by first annealing the samples. We got resistance decrease, grain size increase, and then we test these annealed samples. And what one can see that the curves of annealed and not annealed are very similar in both cases, but the main difference is that both annealed samples, or all annealed samples which we tested, have no resistance decrease in the beginning. So in this way, really your resistance signal can show you such an important information as the change of the grain size. That was what I called side effect. Now let's switch to gold films. Here you see typical microstructure in the beginning, so with 0 cycles. And here you see that they are strongly textured with 1-on-1 texture, which is typical for evaporated gold films. And the initial grain size is shown here, is 200 nanometers. And now, yes, and here this is just a fit cut to be able to stay always on the same place. And then now what happens after 1,000 cycles, you see that the grain growth is very, very strong. We have now average grain size 600 nanometers and more, so it's 300% of grain growth after 1,000 cycles. We have relatively large strains, 1.5%, which is definitely in plastic regime for gold. Then if we go further, 2,000 cycles, even larger grains, and then 5,000 cycles, you see also mechanical damage. Extrusions is shown here, and you see the grain size of 1.5 microns almost. And at 10,000 cycles, we really have an order of magnitude. We start with 200 nanometers at room temperature due to mechanical load, and we end up with 2 micron grains. Okay, so now more interesting question is to understand why. What's going on? So due to strong texture, everything is blue, and it's difficult really to find the same grains in the initial microstructure. If we look at the RT direction, then we have more colors, and you can really spot the coarsened grains after 5,000 cycles and track them back to initial microstructure. You might not see the numbers. There are 10 grains from 1 to 10. I just numbered some grains, and you can find all them in the initial microstructure, which is okay. So it's not recrystallization, it's really grain growth. But the next question is, so what is so special about those grains? There must be a reason why these grains coarsen and others not. And then we try to look, of course, at the grain orientation, for example, because you can have grains which are oriented with respect to the loading direction, so that they have, for example, high Schmidt factor or low Tabor factor or low Young's modulus or whatever, but we have not found any correlation between the coarsened grain with respect to their orientation. Then we looked at the grain boundaries, because everybody or many of you know that the different grain boundaries have different mobilities, different energies, and probably this is the decisive factor which forces the grains to coarsen. But again, here you see different low, high angle grain boundaries and twin grain boundaries. Again, no correlation. We saw all these 3 types moving and all these 3 types not moving. So there must be something special about those grains. And the only thing which we were able to find is they were just a little bit larger, so more than 2 times larger than initial grain size. Which sounds now a little bit trivial, because this is what people usually know. Larger grains grow easier. But then the question again, why? What's the mechanism? And then not so many people can answer it, because I tried. So what's the mechanism? And then we end up with the thermomechanical model. It was kind of stolen from a Gottstein book. Sorry, I forgot to put a link here. So if we imagine 3 grains here, and this is a free energy density. In unstrained situation, they all have approximately the same free energy density. So there is no thermodynamical force. Then if we apply mechanical load, we increase the free energy density by the amount of elastic strain energy density. And then if we assume that For example, grain 2 has higher elastic strain energy density. A driving force will occur for grain 2 to shrink and for grain 3 to grow. This elastic force, this is driving force, is delta P. But then again, the next question, why it should be different? What is behind this? And because of the dependence only on size and not on orientation, we propose the following model, which is based on whole page effect. You know that smaller grains have higher yield stress. So you can imagine that grain 2 has higher yield stress than grain 3 because it's larger, it has more dislocations or dislocation sources. And then, due to the difference in the stress, we have the difference in elastic strain energy. And the driving force estimated for our structures is about 1 to 3 MPa, which is a really sufficient driving force. For many texture transformation, people reported lower driving forces. But also, we have found in some cases that also small grains grow, which were initially small. And those grains had really specific orientation, namely one orientation in the straining direction. And this is the softest direction for copper. Copper is, and gold, both of them are anisotropic material, and one O direction has the lowest Young's modulus. And again, we have here driving force. Grain 3 is soft, grain 2 is oriented. With higher Young's modulus, we can have even larger driving force. So those two we found, but this is the whole page based driving force is definitely the dominant in our case. And then finally something else which is still under, the work is ongoing. What I then realized months later is that if you look at the surface with the SEM, so this is our flip cut, is the same spot which I showed in the BSD. You see, after 1,000 cycles, we have 300% of grain coarsening, but nothing on the surface except of here because of stress concentration. But nothing here, and even after 2,000 cycles, again, only several slip steps. We applied a lot of strain, a lot of plastic strain. So this is 1,000% of plastic strain if you think that 0.5%. And nothing, so where is the whole plasticity? And of course we want to quantify, calculate energies and get more into it, but it looks like grain coarsening really replaces plasticity. So the mechanical energy dissipates by grain coarsening, and in this way you have no damage on the surface. Okay, that brings me to conclusions. What I showed you is very strong grain coarsening by order of magnitude at room temperature induced by cyclic tensile straining. And okay, resistance measurement, I want to make a bit of provocative statement here for people who know what shear coupled grain boundary migration is. We are pretty sure that this concept cannot be used to explain our experimental observations. So it is well proved that it happens, but in our case, all the predictions are not met. So we really think that the thermodynamic force is responsible. And if somebody wants to discuss it or punish me for it, I'm here. I would really love or would be happy to have any discussions in the bar probably. So just find me, I will stay here. Thank you for your attention.